This video is part of a series about recovering the exact values of quadratic irrational numbers from their simple continued fractions. This video is part 1. It is about recovering the value from purely periodic simple continued fractions. We'll set up the problem and define a process for recovering the values. Then we'll work an example. Let's get started. The problem we are talking about here is when we have a purely periodic simple continued fraction, which we can represent like this: r equals r0, r1, r2, and continuing to some r sub n. We use the letter r just because the whole thing repeats. This simple continued fraction repeats indefinitely, so we say it is periodic and we know it represents a quadratic irrational number. Also, this one is purely periodic because there aren't any non-repeating terms at the beginning. Please see this other video about this for more information. What we want to do is find the value of capital R. We could calculate convergence and get better and better approximations, but no matter how many convergence we might calculate, it's still an approximation. We never get the exact value. Here's a different process that leads to the exact value. First, calculate the convergence for one complete period. Then, solve for r using this equation. R equals p sub n minus 1 plus p sub n times r all over q sub n minus 1 plus q sub n times r. That's it. That's the whole process. Now we'll work an example. We'll find the exact value of the number represented by r equals 1, 2, 3. The whole thing repeats, making it purely periodic. Here's the process we just outlined. The first thing we need to do is calculate the convergence for one period. We'll use a table like in other videos. There are rows for k, a, p, and q. We include a column for k equals minus 1, and then it goes up to k equals 2. We won't go through this step by step. We'll just show the results. Here they are. This row has the numerator of the convergence, and this one has the denominator. If you'd like more information about calculating convergence, please see this other video. We'll flash the process again. Now we calculate r using this equation. The numerator equals p sub n minus 1, which is 3, plus p sub n, which is 10, times r. The denominator equals q sub n minus 1, which is 2, plus q sub n, which is 7, times r. Hit pause and review that to make sure you see where the values come from. Now we need to do a bit of algebra to isolate r. First we'll multiply both sides by this, the denominator of the right-hand side, and we get 7 times r squared plus 2r equals 3 plus 10r. Bring all the terms to the left-hand side and set it equal to 0. Now we have 7 times r squared minus 8r minus 3 equals 0. We can solve this using the quadratic formula. R equals 8 plus the square root of 8 squared minus 4 times 7 times minus 3 all over 2 times 7. You might be wondering, what about 8 minus the term with the square root over 2 times 7? That value is negative, so it cannot be correct. Inside the radical, this is 148, so we'll rewrite it like this. We could stop here, but we can also simplify a bit. 148 is 4 times 37, and 4 is 2 squared. So we can pull a 2 out of the radical and factor a 2 out of the numerator and the denominator. This leaves us with 4 plus the square root of 37 all over 7. We'll write that over here too. It's the final solution. This purely periodic simple continued fraction equals this, 4 plus the square root of 37 over 7. We can check our work. A way to become confident our result is correct is to compare the convergence with the solution. For example, we can compare this convergent, 10 over 7, with this value. They're pretty close. 10 over 7 equals about 1.429, and 4 plus the square root of 37 over 7 equals about 1.440. They differ by just over 100th. This builds confidence we didn't make a mistake. We could calculate more convergence and see that they get closer and closer. To be completely sure though, what we can do is take the solution, 4 plus the square root of 37 over 7, and expand it back into a simple continued fraction. The result should be this: 1, 2, 3, repeating. I won't go through the process step by step, but here is what the result looks like. I encourage you to try to do this, and watch this other video, if necessary, about expanding expressions with square roots like this. One important thing to notice is you start with the solution here in the row for k equals 0. And the values of a that we obtain are 1, 2, and 3. These match the sequence in the purely periodic simple continued fraction. We can confirm that the sequence of a equals 1, 2, 3 will repeat because this value here equals this one up here. So if we continued and did a row for k equals 3, we'd get the same results as we got in the row for k equals 0. And then if we did another row, we'd get the same results as we got in the row for k equals 1. And then the same as the results from the row for k equals 2. If we kept going, we'd keep getting a equals 1, 2, 3 over and over. This confirms that 4 plus the square root of 37 over 7 is the correct solution. We recovered the exact value of this simple continued fraction. In this video, we set up a problem statement and gave a process for recovering exact values of purely periodic simple continued fractions. Then we worked an example. That's all for now.